This is the EdExcel AS level maths paper 2 covering the statistics and mechanics section. Question number 1. Sarah is investigating the variation in daily maximum gust T kilonewtons for Camborne in June and July 1987. She used the large dataset to select a sample of size 20 from the June and July data for 1987. Sarah selected the first value using a random number from 1 to 4 and then selected every third value after that. For part A, we have to state the sampling technique Sarah used. Now what's going on over here, we select our first value and we do this by selecting random numbers from 1 to 4, and once we do that, after that we select every third value. And so what we have for part A is systematic sampling. And then for part B, from your knowledge of the large dataset, we have to explain why this process may not generate a sample of size 20. Well, in the large dataset, some days have gaps, and that's because not all data is recorded. And then for part C, the data Sarah collected are summarized as follows. N is 20, the sum of the t's is 374, the sum of the t squared, that's 7,600. And what we have to do for part C is calculate the standard deviation. Now, the formula for the standard deviation is shown here. And so, first of all, what we have to do is calculate the mean of the t's. That's equal to the sum of the t's divided by the number of pieces of data we have, n. So we have 374 divided by 20, and if we work this out, it turns out we get 18.7. And then, for us to calculate the standard deviation, the formula is given by the sum of the t squared divided by n, subtract the mean of the t's squared, and then square rooted. So if we work this out, we've got the sum of the t squared, 7,600, divided by n, which is 20, subtract the mean of t, which is 18.7, then squared. And I square root this. And so if I work this out, we've got the square root of 7,600 over 20, subtract 18.7 squared, we get to three significant figures, 5.51. So we end up with our standard deviation equaling 5.51 to three significant figures. Question number 2. The partially completed histogram and the partially completed table show the time to the nearest minute that a random sample of motorists was delayed by roadworks on a stretch of motorway. And that's what we see here. Now, what we have to do is estimate the percentage of these motorists who were delayed by the roadworks for between 8.5 and 13.5 minutes. Now, what's key in this question is the time is given to the nearest minute. And so, if we take a look at our table, if we have something to the nearest minute, well, here I would have 3.5 and here I would have 6.5. And if we continue, we've got 6.5 to 8.5, and then we've got 8.5 to 9.5, and 9.5 to 12.5, and then we've got 12.5 to 15.5, and then 15.5 to 20.5. And that's taking into account the time given to the nearest minute. Now, because we have a histogram over here, what we can do is calculate the class width first of all. So if I calculate the class width, I've got 3, because I'm going from 3.5 to 6.5. Here I've got 2, here I've got 1, here I've got 3, here I've got 3, and here I've got 5. And if I look at my histogram, well, what we can do is also take a look at the frequency densities. So if I take a look at 3.5 to 6.5, what is that frequency density? Well, we can calculate it by dividing the frequency on the class width. 6 divided by 3, that's equal to 2. And we can do that for the others as well. 17 divided by 1 is 17. 45 divided by 3, that's 15. 9 divided by 3, that's 3. So if I take a look over here, from 3.5 to 6.5, I've got my frequency density being 2. So every 2 squares represents 2. And so here I have 4, 6, 8, 10, 12, 14, 16, 18, and then 20. We can now find out the other information that's missing. So if I take a look between 6.5 and 8.5, that corresponds to a frequency density of 7. And so to find out what the number of motorists here will be, 2 multiplied by 7, that gives 14. And if we take a look at 15.5 to 20.5, we've got a frequency density of 1. And so 5 times by 1 is 5. So we've got enough information to complete the histogram. So from 8.5 to 9.5, we've got a frequency density of 17. So if I add that on, well, here I go up to 17, and then I've got 8.5 to 9.5, that's shown over here. And then we have from 9.5 to 12.5, we've got a frequency density of 15. So 15 is over here. And if I join all of this up, like so. We have our completed histogram. So what does this question ask us to do? Well, what it's asking us to do is estimate the percentage of these motorists who were delayed by the roadworks for between 8.5 and 13. So between 8.5 and 13, what we need to do, well, 13 is, well, here we've got 12.5 going to 13, and then we've got 13.5 to 14. We need to go from 8.5 to 13.5. So that's shown from here to here. And what we'll do is we'll calculate the frequency of this by calculating the area. We've got 1 times by 3, which is 3. So here we've got a frequency of 3 between here and here. We've got our frequency from 8.5 to 9.5. That frequency is 17. So we've got 17 over here, and from 9.5 to 12.5 we have 45. And so therefore, when we come to estimate the percentage of these motorists who were delayed by the roadworks for between 8.5 and 13.5, well, in total, what do we have? Well, we've got 6 plus 14 plus 17 plus 45 plus 9 plus 5, and then between 8.5 and 13.5, well, we've got the 17, the 45, and also the 3, and so we add these together, and then we multiply by 100, and so working this out, we end up with 67.7%, and that's given to 3 significant figures. Question number 3. The Venn diagram shows the probabilities for students at a college taking part in various sports. A represents the event that a student takes part in athletics, T represents the event that a student takes part in tennis, and C represents the event that a student takes part in cricket. P and Q are probabilities, and that's what we see here. The probability that a student selected at random takes part in athletics or tennis is 0.75. What we have to do for part A is find the value of P. So, if we take a look at athletics or tennis, we know that that probability is equal to 0.75. So what I have then is on my diagram, shown in red, the probability of A or T. And all of this is equal to 0.75. Now, we know the sum of probabilities is equal to 1. So we've got all of this, which is 0.75, and then we add on to this 0.05, and then we also add on p, and all of that is equal to 1. And so therefore, we can conclude p is equal to 0.2. Now, for part B, we have to state giving a reason whether or not the events A and T are statistically independent, show you working clearly. Now, using the formula shown here, the probability of A and T is equal to the probability of A times the probability of T. Now, what is the probability of A and T? Well, that's just equal to P. So here, the probability of A and T, that is over here, which is P. The probability of A, well, that is Q plus P. So this is the probability of A, and the probability of T will be this entire circle, which is shown there. So we've got 0.2, and we're questioning, does this equal the probability of A? Now the probability of A is Q plus P, and so we could also work it out by doing 0.75, which is the entire red bit, take away this 0.4. So we've got 0.75, take away 0.4. So that's the probability of A multiplied by the probability of T, and that's P plus the 0.4. So that's 0.4 plus the P, which is 0.2. So this bit is what P is. And so we're questioning, do these equal each other? Well, I've got 0.2 on the left hand side, which is what we had for A and T. And on the right hand side, 0.75, take away 0.4, multiplied by 0.4 plus 0.2. So here I get 0.21. And because those do not equal each other, they are not independent. Now for part C, we have to find the probability that a student selected at random does not take part in athletics or cricket. So we don't want them to take part in athletics, we don't want them to take part in cricket. So what will this be then? So does not take part in athletics or cricket. If I show this on the diagram, we've got just T only and this 0.05. So for part C, we are looking for the probability of not A or C, and so that is what we shaded in green, and that's equal to this 0.4 and then we add to that this 0.05, and it turns out here we get 0.05. 0.45. Question number 4. Sarah was studying the relationship between rainfall, R millimeters, and humidity, H% in the UK. She takes a random sample of 11 days from May 1987 for Luchas. From the large dataset, she obtained the following results, so we've got H and R. Sarah examined the rainfall figures and found that Q1 is equal to 0.1, Q2 is equal to 0.9, and Q3 is equal to 2.4. A value that is more than 1.5 times the interquartile range above Q3 is called an outlier, and for part A we have to show that R equals 20.6 is an outlier. Well, we have an outlier then if our value is greater than Q3 plus 1.5 times the interquartile range. And what we need to do is calculate, first of all, the interquartile range. That's equal to Q3 subtract Q1. And so Q3, we are told that's 2.4 and Q1 is 0.1. And so 2.4 subtract 0.1 is 2.3. And so therefore, if I work out Q3 plus 1.5 times the interquartile range, then I've got 2.4 plus 1.5 times 2.3, and if I work out what this is, we get 5.85. Now our value, that's 20.6, and what we can see then is this 5.85 is less than the 20.6, and so what we can conclude from that then is the R equals 20.6 is an outlier. Now for this particular day, we've got the outlier being 20.6 for the rainfall. Now we have to give a reason why Sarah might include it and then exclude this reading. So first of all, we could include it because it's within the dataset, so we should consider it, but we might exclude it, and that's because it's an outlier, so it could unduly influence the analysis. And then Sarah decided to exclude this day's reading and drew the following scatter diagram for the remaining 10 days values of R and H. And what we have to do for part C is give an interpretation of the correlation between rainfall and humidity. Well, overall what we can see is as one increases, the other sort of increases with it. And so for part C, as humidity increases, rainfall also increases. Then the equation of the regression line of R and H for these 10 days is R equals minus 12.8 plus 0.15 H. We have to give an interpretation for part D of the gradient of this regression line, which is 0.15. And so this 0.15 represents 0.15 milliliters of rainfall per percentage of humidity. And then for the first part of part A, we have to comment on the suitability of Sarah's sampling method for this study. Now, essentially it's restricted because she only uses 11 days in 1 month from one location. But then, for the next part, we have to suggest how Sarah could make better use of the large dataset for her study. Well, here, we could use more data from other UK locations and consider more months for more days. Question number 5. For part A, the discrete random variable x is a binomial distribution with parameters 40 and 0.27, and we have to find the probability that x is greater or equal to 16. So, for part A, the probability that x is greater or equal to 16, that's the same as 1 minus the probability that x is less than or equal to 15. And so, we have 1 minus Now on our calculator, if we go to the distribution submenu using a binomial CD, and then the variable, we've got x being 15, n being 40, and p being 0.27, and working this out, we have 0.949, etc. for the probability of x being less than or equal to 15. And so 1 minus this, if I work out what this is, I get 0.0549, etc. And so the probability that x is greater or equal to 16 is 0.0549, etc. Now, for part B, past records suggest that 30% of customers who buy baked beans from a large supermarket buy them in single tins. A new manager suspects that there has been a change in the proportion of customers who buy baked beans in single tins. A random sample of 20 customers who had bought baked beans was taken. We have to write down the hypotheses that should be used to test the manager's suspicion. Well, we've got our null hypothesis p equaling 0.3, and because we are testing whether there is a change in that, our alternate hypothesis, we have p not equaling 0.3. We have a two-tailed test. And then for part C, using a 10% level of significance, we have to find the critical region for a two-tailed test to answer the manager's suspicion. You should state the probability of rejection in each tail, which should be less than 0.05. Now, first of all, you can see that our significance level is 10%. Now, we have a two-tailed test. And so, because we have a two-tailed test, essentially, what we have, if I draw it out, we have some sort of a distribution like so, and then on either side is where we have the significance level of 5%. Now the reason we have 5% either side, we've got a two-tailed test, and the 5% and the 5% here add up to give the 10%. And what we need to find is the critical region. Now, the way to think of it is, think of us having some sort of a mean, and what we are doing is finding out some sort of a region where we would accept H0 and in these regions here is where we would reject H0. And when it's asking for the critical regions, well, what we're after is some critical region here and here. We'll call this lambda lower and lambda upper. And then here we've got our expected value. And how would we go about calculating that expected value? Well, if I create a new distribution whereby I've got lambda following a binomial distribution, now here I have a sample of 20 customers, and the probability is 0.3, and so the expected value of lambda will be given by 20 multiplied by the 0.3, which is 6. And so here we've got 6. We've got a region around this expected value, this mean in other words, where we would accept H0, and there are regions where we would reject H0, and that's shown in red here. Now, essentially, there are two situations for when we reject H0. The first one, we reject H0 if the probability of lambda is less than or equal to this lower value being less than or equal to 0.05. And what we can do at this point is use the tables. So from our tables, we look at n equaling 20. We are looking down the p equaling 0.3 column, and we're looking for where this is less than 0.05, and it's less than 0.05 here, which would correspond to 2. And so from the tables, we've got the probability that lambda is less than or equal to 2, equaling the value here, which is 0.0355. So that's one situation where we would reject H0. We reject H0 over here when it's less than or equal to 2. So this critical region is 2. The other situation, we reject H0 if the probability of lambda being greater or equal to lambda upper is less than or equal to 0.05. And because we've got a greater than or equal to, this is the same as saying 1 minus the probability of lambda being less than or equal to lambda upper minus 1 being less than or equal to 0.05. And quite simply rearranging, we've got the probability of lambda being less than or equal to lambda upper minus 1 being greater or equal to 0.95. And so what we can do is use the tables as we did before. Where does the value of lambda be greater or equal to 0.95? Well, that's over here, which corresponds to 9. And so, therefore, from the tables, we've got the probability that lambda is less than or equal to 9 is equal to 0.9520. So here we've got the value of lambda upper, which we can calculate. Now, what's happening is this over here corresponds to the 9, and so therefore we've got lambda upper minus 1 equaling 9, and that comes from what we've just mentioned. And so therefore lambda upper is equal to 10. So this value over here is 10. So how does that help us? Well, our critical regions, which are shown in red here and here, we have being lambda is less than or equal to 2, or we have lambda being greater or equal to 10. Now for the next part of the question, we have to find the actual significance level of a test based on our critical region. So what we need to do for part D is find out the actual significance. And for that, we simply sum those probabilities. We sum the probability that lambda is less than or equal to 2 and lambda being greater or equal to 10. So if I work this out, well, this probability I worked out in green before, that's 0.0355. And the probability that lambda is greater or equal to 10, well, essentially, what we have here then is the probability that lambda is less than or equal to 2 plus 1 minus the probability that lambda is less than or equal to 9. So we've got 0.0355 plus 1 minus 0.9520, and working this out, we get 0.0835. Now, one afternoon, the manager observes that 12 of the 20 customers who brought baked beans brought their beans in single tins, and we have to comment on the manager's suspicion in light of this observation. Well, here, because the 12 is within the significance level, that means that the claim is supported. But then, later it was discovered that the local scout group visited the supermarket that afternoon to buy food for their camping trip, and we have to comment on the validity of the model used to obtain the answer in part E, giving a reason for your answer. Well, here, the model is not valid because 20 customers is not representing all of the customers. Question number 6. A car moves along a straight horizontal road. At time t equals 0, the velocity of the car is u meters per second. The car then accelerates with constant acceleration a meters per second squared for t seconds. The car travels a distance d meters during these t seconds. Figure 1 shows the velocity time graph for the motion of the car between 0 and t. And using the graph, we have to show that d equals ut plus 1/2 at squared. Now, first of all, we know that the distance is the area under the graph. So, knowing that the distance is the area under the graph, well, how would we work out the area under the graph? You can see here we've got a rectangle and a triangle, and the height from here to here is u, and from here to here the height is h, say. And so therefore the area, we've got u times by t, so we have u multiplied by t, and the area of a triangle, that's given by 1/2 times the base, which is t, multiplied by the height h. Let's call this equation 1. Now, we know that the acceleration is a meters per second. So, knowing that the acceleration is equal to the gradient of this line here, think of it as change in y divided by change in x. The gradient is equal to h divided by t. We'll call this 2. And so what we need to do is substitute in h into here. Well, if I rearrange, I can see that h is equal to acceleration multiplied by time. And so if I substitute in 3 into 1, then I have d equals ut plus 1/2 t times by h. Now, h over here is at, so we have a multiplied by t squared. And that's exactly what we wanted to show. Question number 7. A car is moving along a straight horizontal road with constant acceleration. There are 3 points A, B and C in that order on the road, where AB is 22 meters and BC is 104 meters. The car takes 2 seconds to travel from A to B and 4 seconds to travel from B to C. For the first part, we have to find the acceleration of the car. Well, let's draw a diagram to model the situation. So we've got the points A, B and C. Here we have 22 meters, and here we have 104 meters. And we know from A to B it takes 2 seconds, and from B to C it takes 4 seconds. Now, what we need to do is find out the acceleration of the car. Now, it's constant acceleration, which means from A to B and B to C, the acceleration will be the same. So, for the first part, if we use S equals ut plus 1/2 at squared, and you can find that in the formula book here, then from A to B we have 22 equals, well, the time is 2 multiplied by u plus 1/2 times by A times by time squared, so that's 2 squared. 22 equals 2u, and here we have 4 times 1/2, which is 2. So we add on 2a, and dividing through by 2, 11 is equal to u plus a. We'll call this equation 1 for now. Now, going from B to C, well, the total displacement will be 104 plus the 22, which is 126. So we have 126 as our displacement, and then the total time then Well, here we would have 6u, because we've got the 2 and the 4. And then we add on 1/2 a times by 6 squared. 126 is equal to 6u plus 18a. And so therefore 21 is equal to u plus 3a. And if I rearrange for, well, I'll call this equation 2. And what we can do is find out what a is by solving simultaneously. And we can do that by working out equation 2, subtract equation 1. 21 take away 11 is 10. 3a minus a is 2a. 2a is 10. A is 5. So we have 5 meters per second squared. And then for the next part, we have to find the speed of the car at the instant it passes A. So it passes A when the time is 0. So if we use v equals u plus at, so using v equals u plus a multiplied by t, when t is 0, we've got v equals u plus 0 times by 5. And that's with t equaling 0. So therefore, we end up with v equaling u. And what we can do is find out what u is by using equation 1. So if we use equation 1, we have 11 equals u plus a, and with a equaling 5, 11 equals u plus 5, which means u, which is what we're finding, is equal to 6 meters per second. Question number 8. A bird leaves its nest at time t equals 0 for a short flight along a straight line. The bird then returns to its nest. The bird is modelled as a particle moving in a straight horizontal line. The distance s meters of the bird from its nest at time t seconds is given by s equals 1 over 10 multiplied by t to the 4 minus 20t cubed plus 100t squared, where t is in between 0 and 10. For part A, we have to explain the restriction 0, which is less than or equal to 10, which is less than or equal to t rather, which is less than or equal to 10. Well, first of all, for part A, we are given s equals 1/10 of t to the 4 minus 20t cubed plus 100 t squared. And if I factorize out a t squared, I've got 1 over 10 t squared multiplied by t squared minus 20t plus 100. And so therefore, we can conclude s is equal to 1 over 10 multiplied by t squared multiplied by t minus 10 squared. And so therefore, what we can see, if we think about the stationary points of this, s will be greater than 0 for t being in between 0 and 10. Now, let's see what happens when t equals 0. When t is equal to 0, we have s equals 1 over 10 multiplied by 0 squared multiplied by 0 minus 10 squared, which is 0 meters. And similarly, when t equals 10, s is equal to 1 over 10 times by 10 squared multiplied by 10 minus 10 squared, which is again 0 meters. And so, therefore, we've got 0, which is less than or equal to t, which is less than or equal to 10. Now what does this represent? It represents the bird leaving the nest and then returning. And then we have to find the distance of the bird from the nest when the bird first comes to instantaneous rest. Now instantaneous rest, that suggests to us v is equal to 0. So first of all, we've got s equals 1 over 10 multiplied by t to the 4 minus 20 t cubed plus 100 t squared. And we know that v is equal to ds divided by dt. And if I work out what this is, we have 4t cubed minus 60t squared plus 200t divided by 10. And if I factorize out a 4, I've got 4, and I can also factorize out a t, so I've got 4t over 10 multiplied by t squared minus 15t plus 50. And 4t over 10, that's equal to 2t over 5. And then t squared minus 15t plus 50, I can factorize that as t minus 10 multiplied by t minus 5. And so when v is equal to 0, because it's instantaneous rest, we've got 2t over 5 times t minus 10 times t minus 5 equals 0, in which case t is either equal to 0, 5, or 10. Now we know that when t equals 0 or 10, s is equal to 0, and so therefore when t equals 5, s is equal to 1/10 multiplied by 5 to the power of 4 minus 20 times by 5 cubed plus 100 times by 5 squared. And it turns out we get 62.5 meters. Question number 9. A small ball A of mass 2.5 kilograms is held at rest on a rough horizontal table. The ball is attached to one end of a string. The string passes over a pulley P, which is fixed at the edge of the table. The other end of the string is attached to a small ball B of mass 1.5 kilograms hanging freely, vertically below P, and with B at a height of 1 meter above the horizontal floor. The system is release from rest with the string taut, as we see in figure 2. The resistance to the motion of A from the rough table is modelled as having constant magnitude 12.7 newtons. Ball B reaches the floor before ball A reaches the pulley. The balls are modelled as particles. The string is modelled as being light and inextensible. The pulley is modelled as being small and smooth, and the acceleration due to gravity g is modelled as being 9.8 meters per second squared. for part A, for the first part, we have to write down the equation of motion for A, and then we have to write down the equation of motion for B. And to do this, we need to use F equals ma. Now, first of all, we've got a resistance force from A, and so if I add this resistance force on, as we see here, we've got 12.7 newtons. And because the pulley is light and inextensible, we have a tension here and a tension here, which are both equal. We'll call them both T. And then we've got the weight of B. So we've got the weight of B, as we see here, 1.5 G. And so, for part A, if I consider the motion for A, we've got T going forward and 12.7 pulling it back. So I've got T minus 12.7, and that's equal to the mass, which is 2.5, multiplied by the acceleration. And if I consider B, we've got T pulling it back, and going forward we've got the weight, and this is equal to the mass, 1.5, multiplied by the acceleration. And then for part B, we have to find the acceleration of B. Well, to do that, we need to solve these equations simultaneously. If I call this equation 1 and this equation 2, we can add equation 1 and 2 together. So by adding 1 and 2 together, we eliminate the t's, and so we are left with 1.5g minus 12.7 on the left hand side. And so if I work that out, 1.5 times 9.8 minus 12.7, that's 2. And on the right hand side, 2.5a plus 1.5a, that's 4a. So I get 2 equals 4a. And so therefore a is equal to 0.5 meters per second squared. Then for part C, using the model, we have to find the time it takes from release for B to hit the floor. Well, here we need to use the Suvat equations. So for part C, we will be using S equals ut plus a half at squared. And so if I write that down, we will be using S equals ut plus 1/2 at squared. I've got the displacement 1, and that's equal to u. Well, it's released from rest, so I've got 0 times by t plus 1/2 times by 0.5 times by t squared. So I've got a quarter equals, rather I've got a quarter t squared equals 1. So I've got 1 equals 1/4 t squared. T squared is equal to 4. T is equal to 2. And then for part D, we have to suggest 2 improvements that could be made in the model. First of all, we could use a more accurate value of G, or we could use variable resistance.